I mentioned again. Okay, so now I show you several examples. Okay, this is the first one. So this is a YN. This is a YN. So if you compare, this is giving YN. Okay, YN in this case just involve one term. Okay, so x squared is a phi 1. X squared is phi 1, and A is a C1. So you compare, if you compare this equation with the previous general equation, phi 1 is equal to x squared, C1 is equal to A. So we only consider one term in this case. Okay, so this is a this is an assumed buckling response shape, but this is not exactly response because A is unknown. We don't know the A value because actually you cannot fix A value. You cannot fix A value because this is a buckling response. You can only give the assumed response shape. The response amplitude is unknown, can be any value. So A is a uncertain value. Actually, A is an uncertain value. It's not a determined value. Okay, so N can be any value actually. Okay, so we assume this value and then we use a standard formula. This is standard formula to calculate the strain energy. Okay, and this is a square of the function. So second derivative must be a constant value 2A. So this is a 2A is a constant value. It's very easy to complete the integration to obtain the strain energy. The strain energy must be a function of the A squared. Must be function of A squared. Okay, not A. Okay, if you obtain the linear function about A, is incorrect. So it must be involve the square of the unknown response. Okay, and then for this case, because we just have one axial force, so for all cross section, the internal force is a constant value. It's same as the applied force. So you can first obtain the total deformation, the total axial deformation, and then multiply total deformation by negative N. It is a potential due to the applied force. Okay, so here we first, okay, don't worry about this term. Okay, you just need to use the second term. This is standard formula. This is a standard formula to obtain the total axial deformation. So we first obtain the total axial deformation, use this formula, but this is a special formula only when N is a constant value over the different cross sections. Okay, so in this case we can obtain the total elongation first, and then the total elongation times negative P is equal to the potential due to the external force. Again, this is a function about A squared, must be, okay? And also, and then we can obtain the total potential energy and take a first derivative. We are able to obtain the equation about one coefficient times A. Okay, A equal to 0 is a trivial solution, and the coefficient equal to 0 is a non-trivial solution. From the coefficient equal to 0, we can obtain the buckling load. So this is a solution. So engine method looks easier, okay, than the equilibrium method. But I want to mention important issue. Actually, the accuracy, the solution from the engine method is usually approximate solution, but the solution from the equilibrium method is always accurate solution. So this is the difference, okay? Because the solution from the equilibrium method is obtained from the solution to the equilibrium equation. So the solution must be accurate solution. But when we apply the energy method, we assume the solution first and leave one unknown in the solution. So if you make different assumption about the buckling functions, the solution will be different. So here I provide you for the same problem. Okay, when we take a different diffraction function, so this is a one diffraction, another diffraction function, and this is another one. So you can use different diffraction functions. And when you use the different diffraction functions, the solution about the critical load will be different, and usually no one is an accurate solution. So how to compare, how to estimate the accuracy? If you want to obtain comparison accuracy, you have to get the solution for the same problem based on the equilibrium method, and then you can have a comparison. Okay, you can have a comparison. So this is a disadvantage, okay, of the energy method. Okay, the energy method is easy to apply because you don't need to mind the sign convention, you don't need to obtain the moment expansion, you just need to obtain the energy. Okay, and the energy is independent of the direction. Okay, so but the disadvantage is it is an approximate solution. Okay, and this is a second example. In here we attach one more spring. So in addition to the strain energy from the structure itself, and also we have a strain energy from the spring. So here for the strain energy we have two terms. This is the strain energy for the column itself. Okay, this is a standard formula. This is a standard formula. Okay, and the strain energy for the spring is equal to the stiffness of spring times the deformation of the spring square over 2. And the deformation of the spring at here is just equal to the deflection at point A. So the deformation of spring actually is just equal to W when X is equal to A. So we can also represent the strain energy in terms of alpha. Okay, so we have two terms in the strain energy expansion, and this is a standard formula. Okay, please do not please ignore the first expansion. You just need to use the second expansion. We can obtain the total axial deformation first, and then multiply the total axial deformation by negative P. We can obtain the potential due to the applied force. So finally, we have total potential energy, and take a force derivative equal to 0. We can obtain the non-trivial solution, which is just critical load. Okay, just critical load. So this is the energy method. When we have one more spring, you just need to calculate one more term about the strain energy from the spring. Okay, from the spring. Okay, now we go to example 3, and I will provide you some discussion about this question. Okay, in this question, okay, the structure. This is a tall building structure. Okay, when we design a super tall building structure, we sometimes also have to estimate how about the critical load. Okay, if the real applied force is larger than the critical load, that means the structure under your design is not safe. Okay, because the structure will become unstable under the real load. Okay, so how to determine this critical load? Because now the load is a distributed load due to the self-weight of the structure. Okay, due to the self-weight of the structure. Okay, in this solution, I provide you the response function. Okay, this is the response function. We don't know A value, so this is just a one term. Okay, this is a C1, this is a phi 1. The special point here is that actually when we do the stability analysis, we can select any point as the origin of the coordinate, and we can place the origin of the coordinate and the direction of the coordinate in any way. For example, usually we take this point as the origin of the coordinate. So here is the x direction. This is the x direction, and this is the y direction. But it doesn't matter because in the equilibrium method, it's very important. Okay, in the equilibrium method, it's very important to define which direction is a positive y direction. But in the energy method, it's not so important. You can assume this point as the origin of the coordinate, or here I put the origin here. It is very special because this is a response location. This is not fixed location. And actually we don't know where is the location at this point. We don't know where is the response? How about the response at this point? Because response can be any value during the buckling. Okay, so the absolute value of the response at the point B actually is unknown, but we can still put the origin here. We can still put the origin here. And then we assume this is the x direction, this is the y direction, and this is the corresponding for this function. Okay, you can construct any function, and the function just need to satisfy the boundary condition. For example, if this is origin, so when x is equal to 0, because this is the origin, so when x is equal to 0, y is also equal to 0, because this is the origin. But for this point, it is not, y is not equal to 0. Okay, at this point, when x is equal to 0, so y is equal to the distance from here to here, and this distance is equal to 8. This is unknown. So you just need to make sure that when x is equal to 0, the response at this point is equal to the distance from here to here. And also you have to make sure when x is equal to 0, the false derivative about y is equal to 0, because rotation here is equal to 0. Okay, so here I just want to show you you can put the origin at any location. Okay, you just need to select the corresponding response function which satisfies the boundary condition. That's all. Okay, so the location of the origin and the direction of the coordinate is not so important in the energy measure. Okay, and then I show you how to obtain the solution. Okay, firstly, we use the calculate the strain energy. So you can see this is a standard formula. So in this standard formula, you don't need to mind the force is a constant force or distributed force, because the strain energy only depends on the response. So when response function is given, you just need to put the response function and to obtain the strain energy. So it is irrelevant the type of the force. Okay, regardless of the force, constant force or varying force. Okay, but when we calculate the potential due to the applied force, you have to use this formula, and you have to obtain the internal force at different sections. Okay, so now I show you how to obtain the internal force for different sections. Okay, so we cut off any cross section. For example, we cut off this section, and because this is the origin location, so the distance from here to here is equal to x. Okay, because this is the origin. Okay, so distance from here to here is x. So, and this is the reason why I put the origin here, because when we put the origin here, it's very easy to count the distance from here to here, it is equal to x. Okay, so when you cut off here, when you cut off section here, so the internal force for this section, if you take the segment above this section as a free body, so you can obtain the force equilibrium in the voltage direction. So the actual force for this section should be balanced by all external forces applied on this free body. So because we have a distributed force, so if you cut off this section, the total force applied on this segment is equal to the distributed force intensity. The intensity is equal to is equal to G. So G times X is equal to the total force applied, right? And then N is equal to X times A, correct? Okay, so this is a force equilibrium. That's all. So you just need to cut off any cross section and take the segment above this section as a free body, and based on the force equilibrium in the voltage direction to obtain the expansion about Nx. So we have a Nx like this. So when this is a function about x, so you have to use a standard formula. You cannot to obtain the total deformation force. You have to use a general formula to calculate the potential energy. So this is a potential due to the external force, and N is a function about x. Okay, it's a function about x. So we can get the total potential and take a force derivative, we can obtain the buckling load. And this buckling load is a distributed load. So based on this formula, so for any tall building structure, we are able to estimate the buckling load. Okay, for any tall building structure, when the self-weight is provided, when the EIA is provided, we're always able to determine the critical load. So now I have a question for you. Okay, we have 3 questions for you. The first question is that when I change the origin from here to here, what will happen? Actually, you can find some examination question in the past paper. We change the origin from here to here. When we change the origin from here to here, okay, the expansion nx will be changed. Why? Because when the origin is here, we cut the same section, and then the distance from here to here is not equal to x. The distance from here to here is equal to a rho minus x, right? So we have to change this expansion. So we have to change this expansion to g times parenthesis a rho minus x. Can you understand? Okay, this is the first question. Okay, now I provide a second question. If I add one more expansion, if I add a concentrated force here, for example, the concentrated force is equal to g times any value, for example, g times a rho. So if I add one more concentrated force here, and then you also have to change this expansion here. Okay, you have to add one more constant value. Do you understand? Yeah. Yes, this is the second case. Okay, and I provide a third case. In the third case, we don't have a distributed force. We have a force like this case. Okay, we have put a force here. And for tall building structure, sometimes we have a very heavy, for example, water tank. Okay, water tanks at the middle of the total height. So maybe we have another force here, concentrated force here. So this concentrated force may be equal to P, or maybe equal to 2P, or maybe equal to 1.5P. But anyway, we have 2 concentrated force. When we have 2 concentrated forces, okay, you have to calculate the total potential due to the external forces, okay, based on the general formula, or because the internal force for this segment is different from the internal force for this segment. Okay, for the segment, for the above segment, okay, the internal force is equal to P, right? And for the second segment, if you cut off here, the total force, although this is a constant value, but it is different from P. It is equal to P plus 1.5 P, something like this. Okay, so for the 2 segments, the internal forces, okay, have a different value, but each one is a constant value. So you can separate the total length of the column into 2 segments. For each segment, you can first obtain the total deformation for this segment, and then times the corresponding negative applied force. For the first segment, it is equal to 1P, and for the second segment, it is equal to P plus 1.5P, something like this. Okay, so I provide you 3 examples. Okay, so already cover all past examination paper questions already. Okay, so here we have 3 cases. Okay, so it's very simple. Actually, in the function examination, I just make a little bit change like this. Okay, just make a little bit change like this. Okay, and maybe you have a question for me. I want to talk a little bit about this question. Okay, so if I change the origin of the coordinate, and this expansion will be changed, right? I just mentioned. So definitely, when we use this formula, the UP, the result about UP will be also different. Okay, so it is possible if this is different, that means the final solution about critical load will be different. It is possible. For the same structure, I just changed the coordinate where I can obtain different solution about critical. It is impossible. So So what is the reason? Actually, when we change the origin, okay, when we change the origin from the top to the bottom, actually we also have to change this expansion. Okay, because this extension is corresponding to the origin here. If you move the origin from here to here, of course, this function also should be changing. Of course, I will provide you a different expansion, and the new expansion about the response should satisfy the new boundary conditions. The new boundary condition means when we have an origin here, so y0 is equal to 0, y dot 0 is equal to 0. That's all. Okay, so when this term is changed accordingly, the final solution must be the same. Okay, the final solution about the critical role must be the same. Okay, and physically the solution should be the same because you just change the location of the origin. This is a mathematical issue. It's not a physical issue. Okay, so this is a solution. And now I provide you more examples. Okay.